What if I told you that deep inside an AI, there's this hidden world, a world filled with elegant geometry? Today, we're going to peek past the code and see how these models build intricate shapes just to figure out something as simple as, well, where a line of text ends. Okay, so it all kicks off with this really interesting puzzle. When an AI, say Claude 3.5 Haiku, looks at text, it doesn't see words like we do. Nope, it just sees a long stream of numbers, where each number is like a little piece of a word. So the big question is, how can it possibly do something visual, like formatting text, when all it's getting is this flat list of numbers? And this really shows you the difference in how we perceive things. On the left, that's what we see, right? Neatly wrapped text. But over on the right, that's what the AI gets. Just a sequence of token IDs. All that visual structure we take for granted, it's gone. The model has to figure all of that out completely from scratch. So let's break down a task that feels totally automatic to us, line breaking. I mean, when we're writing and run out of space, we just hit enter, right? We know to start a new line. But for a model, that simple little act requires this surprisingly complex calculation. It has to actually predict if the next word is going to fit. All right, so this is our first real peek under the hood. Think of this attribution graph as a kind of flow chart for the model's thought process. It gives us the high-level game plan. First, it figures out the line width. Then it tracks its current position on that line. After that, it calculates the distance to the end and uses that to predict if the next word is just too long to squeeze in. So this whole complex process really boils down to 3 key steps. Step 1, the model has to represent its current position on the line. Step 2, it needs to estimate how far it is from the end of that line. And finally, step 3, it uses that distance to predict if the next word is going to fit. And the secret to how it does all of this, it's geometry. Now, to really get this, we have to talk about a concept called a manifold. I know, it sounds super complicated, but just think of it as a really clever way to represent a simple idea, like, say, counting from 1 to 100, as a more complex but super organized shape in a higher dimensional space. Imagine taking a piece of string and arranging it into this intricate, beautiful curve in 3D. That's kind of what's going on. And this is a fantastic illustration of what the model's actually doing. It's not just counting, 1, 2, 3 in its head. For every single character position on a line, it plots a point in its internal high-dimensional space. And get this, those points don't just form a straight line. They trace out this beautiful, complex, almost rippling curve. That's the character count manifold. So you might be wondering, why go to all this trouble? Why this fancy, elegant shape? Well, it's because it's actually the most efficient solution. A simple straight line would be a disaster. The model would have to choose between making the numbers astronomically huge or losing the ability to tell close positions apart, like 41 and 42. This curved manifold, though, lets it keep all 150 plus positions totally distinct and manageable. And what's wild is, this solution is incredibly similar to how place cells work in our own brains. Okay, so the model has this amazing, sophisticated, and frankly, beautiful way of knowing where it is on the line. But how does it actually use that geometric map to figure out when to break the line? How does it get that sense that it's getting close to the edge? Well, knowing your current position is only half the battle, right? You also have to know where the finish line is. So to do this, the model actually builds 2 separate but very similarly shaped manifolds. You've got one for its current character count, that's the blue and purple one, and another for the total width of the line, which you see in yellow and green. The whole calculation really comes down to this one super elegant operation. The secret isn't addition or subtraction. Nothing that simple. It's a geometric twist. And this twist is performed by a specialized part of the model called an attention head. You can think of it like a tiny little sub-processor inside the AI that's just an expert at comparing 2 things. And this is the real aha moment. That attention head grabs one of the manifolds, let's say the character count, and it rotates it. Now, when the character count is far from the total line width, the 2 shapes are all misaligned. But as it gets closer and closer, that little twist causes the 2 curves to line up almost perfectly. And that perfect alignment, it creates a massive internal signal, basically a giant flashing light that screams, hey, you are near the end of the line. And believe it or not, it gets even more sophisticated. The model doesn't just rely on one of these measurements. Nope. It has several different attention heads all performing this twist, but each one does it from a slightly different angle or with a slight offset. What this does is create a sort of stereoscopic sense of distance. Think of it like how our two eyes give us depth perception. It allows for a much, much more precise estimate of how many characters are left. It's just another one of these fascinating parallels to neuroscience, really mirroring how boundary cells work in the brain. Okay, so at this point, the model has a really solid estimate of the characters it has left. But to make that final call, it needs one last piece of the puzzle, the length of the very next word. So in its final layers, it represents both of these key pieces of info to set up the final showdown. And this is where we see the final geometric masterstroke. The model doesn't just have these two numbers floating around. It very deliberately arranges them in its internal space so that they are almost perfectly orthogonal. That just means they're at a 90-degree angle to each other, just like the x and y axes you'd see on a graph. And why does it do that? Because this orthogonal setup has a truly brilliant result. It takes a pretty complicated question, is the length of the next word greater than the space I have left, and turns it into a dead simple one. The answer becomes just a straight line. Everything on one side of that line means, yep, it fits, and everything on the other side means, nope, time to start a new line. It is just a remarkably elegant solution. So what does all of this tell us? What has looking at this one simple task actually revealed? Well, for one, it shows that the early layers of a model aren't just crunching data. They're performing really sophisticated perception. Second, it shows that geometry is an incredibly powerful language for understanding how these AIs actually compute things. And maybe the most fascinating thing of all is that these models can independently come up with solutions that are strikingly similar to what nature figured out ages ago, hiding these absolutely beautiful mechanisms inside the most boring everyday tasks. I just want to leave you with this final thought, and it comes straight from the researchers who did this work. They suggest that instead of thinking about these early layers as just processing data, we should really think of it as perception, that the very beginning of the model is responsible for seeing the input. And that's a pretty profound shift in how we think about this, right? It suggests that deep inside these machines, a completely new kind of sensory world is starting to take shape.